In this lecture, we'll discuss what properties of extrasolar planets we can measure and how extrasolar planets compare with the planets in our solar system. Despite the challenges of detecting extrasolar planets, we can actually learn a surprising amount about them. Depending on the technique used, we can get at properties like orbital period, distance, shape of orbit, mass, size, density, and even a little bit about a planet's atmosphere and temperature. We'll take a look at each of these properties and how astronomers are able to figure them out. The Doppler shift data can tell us about a planet's mass and the shape of its orbit. This is Doppler shift data for two stars. They both have similar periods, meaning their planets should take about the same amount of time to make one orbit. The star on the right, though, has a big radial velocity. It must therefore be more massive. These two stars have similar radial velocity magnitudes, so the mass of their planets must be similar. But the star on the right has a shorter period radial velocity curve. This means the planet is closer to the star. Now the star on the right has an asymmetric radial velocity curve. This tells us that the planet's orbit is not very circular. It's highly eccentric. We can only detect the Doppler shift if some part of the star's velocity is toward or away from us. The more the orbit is tilted towards edge-on, the greater the shift we observe. The Kepler-11 system is a great example of how we can get at orbital periods and planet sizes. Each downward dip represents a transit where the planet is blocking some of the starlight. Astronomers have studied this system and found 6 different planets transiting the star with periods ranging from 10 to 120 days. These plots show the transit of each planet in more detail. The size of the planet is calculated from the depth of the dip. The more distant planets have wider dips because they orbit more slowly, so their transits take longer. Believe it or not, we can even get at the density of the planets. Remember, density is an object's mass per volume. The Doppler method can give us planet mass, and the transit technique can give us planet size, or the planet's radius. From the radius, we can calculate the volume. We can get at density. And density offers clues to what the planets are composed of. We can get more information about a planet's atmosphere from the transit method. When the planet moves in front of the star, it's like its atmosphere is in front of a hot light bulb. This means absorption lines from the planet's atmosphere will show up in the spectrum. We can get elements in the atmosphere from that. We can also measure the system in the infrared when the planet and the star are both visible, and then measure the system when the planet is behind the star. If we look at the difference, we can get an idea of the planet's temperature. The number of extrasolar planets that we've looked at is now large enough that we're beginning to gain insight into how these planets compare to our own solar system. And some of the observations are not what we expected. There are 2 key orbital properties that help us understand the layout of extrasolar planetary systems. The average orbital distance, which allows us to compare locations of planets in other solar systems to the location of planets in our own, and orbital eccentricity. This allows us to determine how much the orbits in other solar systems differ from the nearly circular orbits in our own solar system. This is a graph showing the 2 key orbital properties for over 500 extrasolar planets. Average orbital distance is on the horizontal axis, and orbital eccentricity is on the vertical axis. The sizes of the dots indicate the mass of the planets. 2 major things to notice. First, most of the extrasolar planets orbit their stars more closely than Mercury orbits the Sun, and none are as far out as our Jovian planets. The second thing is that orbits of some extrasolar planets are much more elongated than those in our solar system. Mercury is the most eccentric planet that we have. This bar chart shows the numbers of planets in different size categories detected by the Kepler mission. They all have orbits of less than 50 days. There's a general trend towards smaller planets being more abundant than larger planets, at least down to the size of a couple of Earth radii. The trend likely continues to even smaller worlds, but we can't be sure because these tiny worlds are at the limit of Kepler's measurement sensitivity. The actual numbers of small worlds is probably much larger. There are a few conclusions we can make. First, extrasolar planets show much more variety than the planets of our own solar system. For example, we found a planet that has the density of styrofoam and another that has the density of lead. Second, many planets appear to be terrestrial in nature. This is an artist's impression of a sunrise over what's known as a super Earth. This world is about 70% larger than Earth and rocky. It could be the remains of a Jovian type planet that got too close to its parent star. Third, some planets are not clearly in the terrestrial or Jovian category. This planet is an example of a super Earth. It's orbiting a red dwarf star about 40 light years from us. Observations from Hubble show that it's a water world. It's enshrouded by a thick, muggy atmosphere. This is a new type of planet. It's like nothing we've seen in our solar system. Finally, we can't ignore the effect of orbital distance on a planet's nature. Hot Jupiters could have all sorts of interesting features, like clouds of mineral flakes or steamy atmospheres. The bottom line is that extrasolar planets are abundant and diverse. I encourage you to explore the Kepler mission website. There you can find all sorts of fun information about the plethora of planets we've found. Take care. I'll talk to you soon.